そうですね。Doesn't matter. Oh, really?
This is a Russian trick.
Ah, fine. Yes. Okay. So we were looking at the image of Gauss map, Schwarz map. That I mean defined by H upper half plane to so use that. Sorry. Yes, upper half plane to somewhere, or even maybe it's better to no, maybe it's there is no need to specify. Yeah, and this was a ratio of two hypergeometric functions. F1 at F2Z. Defined like this, and so this we were the situation like this. So 0, 1, infinity. Say infinity. These upper half plane will be mapped by means of the Schwarz map into curvilinear triangle with angles defined by theta 0 equals 1 minus gamma 2 pi at 1 maybe gamma minus alpha minus beta, isn't it? So far as I remember. Let me check again. Oh, I should bear my glass. So these are ratio of two hypergeometric functions whose behavior, asymptotic behavior around 1 is determined by their monodromy around hemidromy. So yes, it is gamma minus alpha minus beta to the pi, and theta at infinity, it is determined by gamma minus alpha or alpha minus beta or something like that. I check it. Yes, alpha minus beta. Yes. So there, and curvilinear triangle by U Gauss Schwarz map. So Z is here, and U will be here. So now there were three cases. There are three cases that we studied. That is, first one was spherical case, maybe. That is, say, theta 0 summation is greater than 1. Second Euclidean case, summation is equal to 1. That is the usual triangle we get on the plane. And third one is hyperbolic. That is that the most difficult one, theta 0 plus theta 1 plus theta infinity strictly smaller than 1. That is that I drawn here. Yeah. So this is the most difficult case, yeah, to study, because so the spherical case and Euclidean case we look at it. Look. So when the summation is, for example, 1 over n and 1 over n, and 1/2 and 1/2, yeah. So 90 degrees and pi over n. Then we got tiling of a sphere by means of this. So this is the image of the upper half plane, and the complex by Schwarz reflection lemma, we get the lower half image of the lower half that is completely determined as complex conjugate to this map. So, and now we pass to the analysis of the hyperbolic case. That is, say, smaller than 1. For example, or maybe example we can look at later. So to analyze this situation, we need to recall some facts about cross ratio. Cross ratio. So, in fact, it is kind of introduction to hyperbolic geometry. That is, say, geodesic is geodesics are circles. That is, say, circles in wider sense of word. So, and to see this, we need to recall some fundamental facts on the cross ratio. Cross ratio is given by, so let us y1, u2, u3, u4 define as u1, u2, where is it? Yes, u1, u2, sorry, we3, we4, divided by u2 minus u3, u2 minus u3, u4. This is the definition of cross ratio of 4 points for complex numbers, or including infinity, of course. And we shall further denote by s of z, say f of z equals z for fixed u2, u3, u4. So now it is a function, rational function is that. So u2, u3, so this is number, and this is a rational function, okay? So, so what is remarkable in this, this cross ratio? It is real, so S of, say, one thing that we recall is that for t, tu, that is, say, au plus b over cu plus tz, c plus d, linear transformation, for every linear transformation, tu1, the tu1 tu4 after transformation, no, maybe it's simply I write tu, it is equal to the cross ratio itself. So of course ABCD okay, and so this is one fact. Secondary important thing is that this cross ratio is real. Cross ratio, yes, okay, cross ratio, it is real. Maybe I can denote some, okay, cross ratio. Cross ratio. Cross ratio is real. Is real if and only if u1, all these uj are on a circle. On a circle for all j. This is a remarkable fact about this cross ratio. Two facts, two fundamental facts that we shall use all the time. To see how this kind of curvilinear triangles cover cover the image. Yeah. Cover the image. In fact, it covers upper half plane. Yeah. So and we can introduce a distance. Distance between on a upper half plane. Distance between between 2 points, u1 and u2, on the upper half plane. Yeah, this is upper half plane is our hyperbolic. So this distance is defined in the following manner. Distance of yeah. So let us consider before introducing distance. Let us consider this cross ratio. U1 complex conjugate U2 bar. Okay, this kind of. So what is it? U1 U2 U1 bar U1 minus U2 bar, isn't it? Yeah, in case U1 bar minus U2 something is U1 bar minus U2. Yes. So I shall apply this formula. Maybe it's better to write it here. Yeah. U1 bar U2 bar. This number shall be real if so U1 and U2 if U1 and U2 are located on a circle. Huh? So this is yes, I'm right. Yes. So U1 minus U2 over U1 minus U2 bar. U4 U2 bar. Okay. Divided by U1 bar minus U2 U1 bar minus U2 bar, isn't it? That is, say U1 minus U2 times U minus U2 bar divided by U1 minus U2 bar and its conjugate. Its conjugate. That is, say it is U1 minus U2 U1 minus U2 bar square. Okay? Yeah, so this is real number. Real positive number. Say, yeah. So it's a positive number. So we can consider the square root of it. So that is the definition of the distance. So if we get positive real number, it will be natural too. So this is d of u1 u2 equals to square root of this. That is, say u1 minus u2 over u1 bar. No, u1 minus u2 bar. u1 minus u2 bar. No, 4 is this one. U2 bar, yes. Okay? You see it? Now I pass to infinitesimal distance. That is, say, consider that I have d of u plus du, something very small, and the u. Yeah, this is not good, maybe. Yeah, the distance may. Yeah, okay. So that is, say, the upper denominator I have the u, and the numerator I have u plus du minus u bar. Hmm? It is imaginary part. If I write x equal iy, imaginary part of u, then it will be 2iy plus something very small. That is, say, equals this. That is, say, y is, if y, always we consider y positive. Hmm? That is, say, so it doesn't matter. So infinitesimal. Hmm.
I mean, we can compare it to metric space.
Yeah, that we introduce some metric. But y is not positive, so we can we erase this. So this is the du over y. Yes, that is y is. Oh, if we want, so we can introduce infinitesimal. So to define a geodesic, we shall define which the integral that we shall integrate. That is, say, the distance. Okay, now distance between 2 points will be minimum of this integral y over du is yes. So it is minimum of this integration path, this value integral along this integration path. That is, so this will be the definition of. Yeah. So this is the hyperbolic distance introduced on the upper half plane. So now now I want to argue the following, that we saw that last time we saw that this action, as I said, the monodromy action, lambda f1 bar over f2, that is, say, something a times, that is, say, no, in fact it's a uz times u1, maybe yes, something f1 f2, and maybe I can write it u and 1 simply, yes, instead of considering a f1 plus, where is it? Yeah, this is somehow au a b c d times u1. It is projectively equivalent to a times f1 f2. Okay? And this one was, so this matrix here in this situation was from SU11, but it has been shown that this is L2R by the argument of Lie algebra isomorphism between Lie algebra. So in fact, as A, we can consider it SL2R. Yeah. SL2 somehow there exists some SL2R for each matrix from the monodromy group associated to hyperbolic case. You can find so SL2R matrix. Yeah. So deliberately we identify somehow this matrix and this matrix. So there is some correspondence, but it's an isomorphism. So let us, in fact, I will use this fact, and SL2R acts on A of SL2R. SL2R acts on the upper half plane exactly by this AU plus U goes to AU plus BU CU plus D. Yeah. AU plus B over C. So I consider this this one was AF1 plus BF2 over CF1 plus DFU F2, but it is the same as this if you divide by F2 and numerator and denominator, both of them by divided by F2, then I get exactly this expression. Okay. So now the monodromy transformation of our hypergeometric group is identified with some element of SL2R, very specific, and they must form a kind of discrete subgroup of SL2R. That is. So monodromy, hypergeometric monodromy group must form a discrete subgroup of SL2R. Yeah. That is our further object of further study, and to see this. Somehow, so it is easier to somehow to visualize the action of this monodromy group and clarifying the fundamental domain. For example, fundamental domain. So fundamental domain exactly up to fundamental domain is somehow polyhedron, polygon that is obtained as a union of image of upper half plane, that is image of upper half plane, and this is image of lower half plane. And they are so conjugate in the sense of in the sense of circular cross ratio circular geometry. So maybe I can recall it briefly. What is the yes. So say that the conjugate, there is a notion of conjugate with respect to circle. So conjugate with respect to real line, that is also circle. It is a very special case. Yeah, that everyone knows. But maybe you have heard that there is a notion of conjugates. Conjugate with respect to a circle. So this is a special case, circle. In general, we have this kind of construction. So the definition of conjugate is the following. To U3, U4, the conjugate, that is say SU star, isn't it? This is the conjugate, must be defined like U1, SU of conjugate. That is say, cross ratio consider the conjugate. Then there must be some U star whose cross ratio coincides with this conjugate of cross ratio. That is the definition of U star, defined by this relation. So that is say, if I have image of upper half plane, U star here, U somewhere here, U. Then the image of H lower half plane will be conjugate of this triangle with respect to this circle, this arc, yes. So here I will have U star. So this is a construction somehow of image of the Schwarz map of entire complex plane, C complex plane. Yeah. So that yes, in this way, the monodromy group so our task is to continue. So this is one domain. If we are lucky, we will get a fundamental domain, and then later in applying monodromy action to these domains, to this domain, to these domains, so they are subject to the same monotomy transformation, and so we can get other other domain like this. And then I will have other. So this transformation will be the monotomy action. In fact, we already calculated even monotomy action on the level S1 1. So now, one thing that we shall care about is the following fact, that distance, so we deliberately use linear transformation, projective linear transformation, and we use this fact. So the cross ratio does not change. Cross ratio does not change under the action of projective linear transformation. Yeah? So these T, so T, let us consider T transformation from SA2R real. T let then T real, T is less SA2R. Then U1, also this one, these are sorry, so these are cross ratio, no. Cross ratio, this on a circle, yes, this on a circle, that is so I shall interpret this, this fact that these are real, that is, it is equal to T of U1, TU1 bar, TU2, TU2 bar. Because T is real. So TU, of course, you have here bar, but in fact it is the same. Yeah? Yes. Huh? TU2 conjugate equals to TU2 by itself if T is real. Yeah. So if these are real, it means that U1, so imagine that U1, U2, you have 2 points. And maybe it's better to U1, U2. And we have complex conjugate, U1 bar, U2 bar. And they must, if it's real, then they must lie on the same circle, isn't it? But circle, that is they're on the circle. And here, of course, it is orthogonal to specially chosen circle. That is a real axis. circle that is, they are, in fact, this U1 and U2 are on a circle, are on a circle, orthogonally perpendicular. To real line circle. To U1 and U2, they are on a circle, but it is in a circle that crosses, that intersects with the real axis in a orthogonal. So, okay, this factor is quite important. And now, so the fact that we want to see that, in fact, the statement that I want to establish is the following. That is, say, this triangle so this say theorem is that curvilinear triangles, the size of a curvilinear triangle are located on a circle that is orthogonal to special circle. So that is, say, in the case of, in fact, this formulation is invariant with respect to GL2C transformation. That is, say, it is not necessary to consider this transformation on the upper half plane. So why upper half plane? Maybe SL. You see that SL2R. This if U is SU2R, as imaginary part of U is positive, then AU plus B. So AU. How shall I denote it? AU plus B over CU plus D. This is also positive. This must also be positive. Imaginary part of AU plus B CU. So now A, B, C, D are real, huh? SL2R, huh? SU bar D CU bar plus D. So that to have on the denominator real number. Imaginary part of this AC U square plus what is it? ADU plus BCU bar plus BD. What is it? BD. AC. What is this? So that is say AD. So U equals X plus IY. And so this only imaginary part comes from here. Yeah, all others are real. That is say real AD minus BC. It must be like this. AD minus BC times Y, isn't it? Over that is imaginary part, but AD minus BC 1. Then Y is positive. That is say the image of a point on a half plane by this SA2R transformation will be anew on in the up half plane. Okay, so that is say we can, if we begin from triangle that is located in a up half plane, then under the monodromy action, all the time it will remain on the upper half plane, on the upper half plane H. But yeah. So and now, so if you consider curvilinear triangle, if they are in an upper half plane, okay, so there are almost at least two models in in upper half plane. The circle is that is equal to real axis. That is outside of H. That is outside of H. So it's a kind of boundary, so limit points of this H. Okay, so now yeah, the point is that so this statement says that the following. So if I have some curvilinear triangle, then it must be so this one, it doesn't look like maybe something like this, rather something like this. It's a bit strange, but at infinity, yes. In any case, so that this statement will illustrate it, we have this curvilinear triangle. The side can be continued. This is theta 0 pi, theta 1 pi, and continues such that it attains points on the real axis where this intersection is orthogonal, and in a similar manner like this one also. Its side and say this one also. So this is on the yes, on the upper half plane. Now, maybe it's better to recall that every so after this. Where is it? After this measure, this distance measure, definition of distance, so what is this? That's the point. Yes. That's the point. So this distance. So we want to show that in fact these circles are the circle that intersects with the real axis. This special chosen circle that is real axis. It is geodesic. In fact, we want to see that this circle, this arc. So consider two points, U1 and U2. U1 and U2. U1 and U2. The arc. So U1, U2 on a circle that intersects orthogonally with real axis is geodesic connecting geodesic U1 and U2 U1 and U2 after the definition of a distance, this distance U1, U2. U1, U2 that has been defined. Yeah, this one, so I can write it. It's the minimum of U1 to U2 of this integral. This integral. So they say this integral. So U1 and 2, there, of course, there are various curves that connect U1 and U2. But the minimum of this integral is attained if you consider this integral along this circle. Yeah. So this is also a kind of proposition. Proposition, yeah. So to show this, maybe what is it? We shall look at invariance of distance U2 with respect to the action of SL2R. In fact, so okay, first the arc is secondly, where shall I write second statement? Second statement. Maybe I can write it here. Second, or the proposition is that distance of U1 and U2 is invariant with respect to the transformation by SA2R. Oh, so sorry, TT. SA2R. This second statement. So that is say, in fact, yeah, I think that this one, from this one we can follow. Let us see. With either this, the consideration is following: distance between I times y1 to I times y2, that is say located it is easy to calculate, and this after that is say distance it is nothing but y over dy. So dx, there is no dx, and u1 u2 minimum. Of course it must be positive, yeah. Du mean that dy, let me say y2 y1 and y2 than y1, and dy, let it be dy positive, dy. That is say it is logarithm of y2 over y1. Yeah. So in this case, it is very easy to calculate. Y1, y2, every so choice y1. But so every u1, u2, you choose any point on upper half plane, u1 and u2. Okay. For every pair of points U1, U2 on the upper half plane, you can find there is this transformation SF2R such that y equals to ty1, ty2. Yes, tt is this SF2R. Yes, real, yes. Such that also in SF2R, such that the image, these 2 points are image of y1 and y2. So, and if it is invariant, that is say, and T, this is also arc, and a geodesic so this segment, T of this segment will be, of course, a circle. And as this has been orthogonal to so these are these 2 points are located on a circle that is perpendicular to real axis, and T is gives rise to a conformal map. As T is a conformal map, that is say the circle. So T of R is of course T of R itself is R itself. The real axis goes to. So T of this imaginary I times R, say I times R, will be the circle that is passing through U1 and U2, but it must intersect with the image of TR, image of R, that is TR, R itself now, in a new image. It must intersect in a perpendicular manner. That is, say, so T of IR intersects with T of R perpendicularly. Yeah, so this was evidently this is this is geodesic, of course. Yeah, that is. And now, so after the rule 2, proposition 2, we get this one also is geodesic with the same distance. With the same distance, that is the value is logarithm. Maybe I can write like this. In fact, well, not smaller than y2, this formula is valid. Yeah? If so, this is without any restriction on the order of y1 and y2. This formula is correct. So now let me pass to the proof of this fact. Proof of this fact. So this answer, yeah, this is somehow a fundamental notion. So proof of 2. The second statement that yeah. So now to yeah, before passing to proof 2, maybe I need to pass to this H model to upper half plane model to unit circle model. Yeah, unit circle model. So H model, upper half model to unit circle model, unit disk model. Sorry, unit disk. So this is U. That's the imaginary powers of U positive. It will be mapped into unit disk by the following: U plus V. Let me denote it with unit disk model, unit disk. Let I say V equals. Last time also I wrote. Consider this kind of fractional mapping, projection mapping. That is, say, V of U, say this is V of U, and V of what happens? So, imaginary part, let us check what happens with these points. So where 0 goes to minus I, think. Yes, minus I. V of I goes to 0, of course. V of infinity goes to I, isn't it? And the image is a circle, of course, because it's the image of the real line shall be a circle, and you can verify it easily that the image is this. So this upper half plane is mapped into unit disk. Now you can see it quite easily. So V of u, what happens? That is u minus I u plus I. And if u is real, then both of them are same. The same. That is, say, equals 1. So it comes here. They are complex conjugate, these denominator and numerator. So the modulus is 1, absolute value is 1. So it is this part, the boundary with real. Transform it into this. Okay, so in fact, working on so this statement, size of a curvilinear triangle, in not now this statement is valid in the disk, in a unit disk, say D, I can write. Let me write it. Unit disk D. D capital, or a circle that is orthogonal to a special demonstration. Now, that was real axis, but in D model, and that is say V unit circle. So what we have drawn here can be translated into unit disk model. So this one, yeah, in any case, these so this circle that was perpendicular to, so maybe it will go to infinity. So V of infinity's image equals 1. So this must be something like this. I. The image must be something like this. Infinity. V over infinity. This one's. So T. This one. It has 2 intersection points with T of R. Here I have 2 intersection points. Yeah, that can be transformed into the points in unit disk model. That is, say I have this one. So if you want, I can denote it. I don't know, alpha 1, alpha 2, it's in U, and now I came to V by this map. I can say V of alpha 1 and V alpha 2. That are on a unit circle. Yeah, these two. But the image of the circle will intersect with the boundary of the unit circle, that is the unit disk, in a perpendicular manner. Okay, thanks to conformal, the property as a conformal map. Okay, so in fact, this use of this model is somehow useful because, several points of view, from several points of view. Where is it? And here also that you want the distance. So I read the detail, but so here we had this distance duy. That was metric. That is metric. But on this model, it will be dv 2 times dv 1 minus v square. The metric on D. This is metric on, so hyperbolic metric on D. This is hyperbolic metric on upper half plane. Okay. So the conformal map of a unit disk to itself. In fact, okay. I think that I can explain it very quickly. Yes. So this is a kind of exercise. And so for this now it's simply you use this replacement, you get this. This metric here on a hyperbolic plane, on a unit disk. As you see that as v tends to 1, it never attains 1. V square never becomes 1. And it is similar to y never gets to 0. So now the conformal map, and this fact is also where is that? Is it that one? Proposition that in fact there is every conformal map, a conformal map from D to D, say T alpha something V to another point in D is written by so composition of this for some alpha can be written by first one like this fractional transformation, that is alpha is inside of and a disk. So T alpha of alpha equals 0. T alpha equals 0, and you see that it really maps from so alpha is somewhere here, and this map alpha goes to the origin, and the unit circle will again comes to unit circle. Here you can see. I think that you can see quite easily, isn't it? Let me see. V. What is that? V and V alpha over V bar. So this modulus is V1 minus V bar alpha over 1 minus V alpha bar, and the V bar is 1 for all V on a circle on a V minus, so V and V bar, wait a minute. So I use this V minus alpha, and now instead of alpha is V times V bar alpha, because V times V bar equals 1 here on the circle, unit circle. So I can write this expression in this manner. And now you see that if you take this, then it is 1, and this is also 1, because isn't it? No, these are complex conjugate. 1 minus V bar times alpha, and the complex conjugate of this equals V times alpha bar. So these are one another complex conjugate, and the modulus is equals 1. So it is 1. This shows you that so unit circle goes to unit circle here in V. Okay, you see? So this is somehow the conformal map from D to D. The boundary is you see that is what 1 to 1. So written by this, and rotation. The rotation. That is, in general, conformal map, it will be e to the power I theta some times T alpha of V. this will be the most general form of every conformal map that sends unit disk into another into the unit disk. So this is somehow very convenient representation. So now let us consider. I want to show this. I want to show this. I want to show this. So rotation keeps proof of 2 show it for t equals t alpha equals t alpha v v minus alpha over 1 minus alpha bar v. Let us do it, because the rotation is very it is evident that it keeps the distance. It does nothing. So dv, let us look at the derivative with respect to dv. That is, say it is 1 minus alpha bar v square minus v minus alpha times derivative of this minus alpha, isn't it? That is, say it will give us alpha bar v cancels, alpha bar times v cancels. That is, say it will give us 1 minus alpha square 1 minus alpha v square. That is. So, and now on the other hand, I calculate this one. This would give us, so let me, 1 minus alpha times v, let us make it 1 minus alpha times v square minus v minus alpha. Oh, maybe it's better to write it down in such a manner that 1 minus alpha v bar complex conjugate minus v square, the modulus, v minus alpha times v bar minus alpha bar. This is this expression. The result of this expression. So what happens? So 1 plus 1 minus 1 minus alpha bar v plus alpha v bar plus alpha bar v square, isn't it? Minus v square minus alpha square plus alpha v bar plus alpha bar v. Alpha bar v. So they cancel, alpha bar v, and they cancel here. Denominator. and alpha verb v. So something, this part remains, this part remains, but it is evidently, it is denominator I 1 minus alpha square times 1 minus v square. Yes. So only this part and this part remains. And yes, it is equal to 1 minus alpha above v square. Yeah, this is the result. In fact, this is this 1 minus t alpha v square equals this. This. Then, now, the upshot is the following. To show this, dv dt alpha v divided by 1 minus. So, this one is imitation of, where is it? This one, yes, this. So, the metric on d was 1 minus v square dv times 2. So, on the image of by yes, after I read it here maybe. Yes, this is t alpha v. Consider this expression in t alpha v. So this is t alpha v square, isn't it? So dt. So this one will give us the metric of image unit disk, and after this calculation you see that so this one cancels, and finally what happens, maybe this DVD. Let me put this nonetheless, because du, I have this. Yeah. Let us put there. So 1 minus alpha square. So this one divided by this, if you want. So what I need to calculate is this one. So alpha, this is always positive because alpha is an disk. So and this one also cancels. What remains is nothing but 1 minus v square. That's all. That's all. But if you look at this, it is equivalent to this. Isn't it? So what does it mean? The distance, it is nothing but this. So where they say T is a composition of for every T alpha it is 2. Distance between T alpha, this means that distance between distance between U1 and U2 is equal to distance T alpha U1 and T alpha U2. Yeah? for every alpha. And every so conformal map is nothing but a composition of the alpha and the rotation. And both of them keep this property. That is, say, we have proven this on actually we used rather unit disk model than a hyperbolic model, but the result is completely the same. Yeah, that's, so we have shown this. That is, say, we have shown that every so this one, yeah, the arc you want so arc connected on a circle that is perpendicular, that will intersect with the real axis perpendicularly. Hyperbolic length of this this arc is the length of geodesic. Yeah, it is the geodesic. So in this model, we have shown that these hyperbolic in a hyperbolic space, this curvilinear triangle that is image of Schwarz map. With boundaries, that is, with boundary that arcs of this type. That is, say, we have, okay, so at last I can draw some I can illustrate some pictures. So we have seen that, yeah, for example, if, so the point is that these three angles, theta 1 plus theta infinity is smaller than 1. When it is 0, 0, 0, 0, 0, 0. 0, 0, 0 cases like this. And yeah, so here I have, so this angle is 0, and it intersects every and so on, so getting smaller and smaller. So maybe this one and this upper half plane, image and lower half plane, and then later it continues. And this is so this is a unit disk. And I illustrate all this construction. So this curvilinear triangle, that is image of upper half plane. So it is, you can say, unit disk model of a hyperbolic plane, hyperbolic space, of the hyperbolic space, maybe the hyperbolic space, with metric 1 minus v square over dv 2. This is a metric defined on this v on a unit disk, open unit disk, and this one was the image of so infinity. Not really. Hyperbolic. Maybe this is the hyperbolic geometric function cannot be realized. So because the exponent is. So let us see other more realistic. So hypergeometric. Hypergeometric 2, 3, infinity, 237. Yeah, 237. That is, say, theta 0. The summation is smaller than 1. Smaller than 1, then I have triangle. So I have heptagon, I think. How many? Any case, so this is a fundamental domain, and this is so upper half plane and lower half plane, and after, so this kind of and you get the heptagon here. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Yes, heptagon. 7, and this continues, and it will fill the unit disk. Yeah, here I have the picture. So 7, of course, comes from here, heptagon. So this angle, this was 7 over. This was 7 pi over 7, isn't it? Pi over 7, and here I have pi over 2, because the angle of the triangles is 0 times pi is the angle, and here I have pi over 3, such kind of triangle. That is the image of the upper half plane by U. And yes, I have pi over 7. That is, say, this triangle in together with the image of lower half plane. I will have here angle 2 pi over 7. 2 pi over 7 here in this. And make a term, moving term. Then I will have 7 So seven times this triangle will cover this heptagon. Yeah. So this is also hyperbolic unit disk model, and this one, of course, can really be realized as a hypergeometric function, the image of the Schwarz map, a hypergeometric Schwarz map. Yeah, so is it. Yes, yes, H.A. Schwarz, yes. Many quite important, non-trivial, for example, Schwarz reflection principle, or if holomorphic function, anti-function, is real on a real axis, then f of z bar is fz over bar for f x real valued for a holomorphic function like this, and Schwarz lemma, and so on, many. And many of them are quite related. Yeah, this fact is used to construct this, so to unite the upper half plane triangle and lower half plane triangle. Yeah, and to get one triangle, one polygon that has been used here in this. Is a student of Weierstrass. Okay, so next time I will pass to the Pohama hypergeometric functions. Monodromy of Pohama and the application to maybe mirror symmetry. Yeah. Okay.